All right, welcome. Have our first participants rolling in. See, we got Mike and Connor and Gregory. You guys get the award for being the first to arrive. Hey, I recognize a lot of these names. All right, I see people getting connected. This is a little bit different today because we're used to working in teams, and today we have a Zoom. So to break free of some of our government regulations and requirements for cybersecurity, but to have a little easier platform to work with for this event. So we'll give people a couple more minutes and then we'll jump right in. We'll allow people not to be relying on their phone for the perfect time. Let them go by that watch. And there's Jonah joining us and Tamina. And who else am I missing? Ah, Solomon. Yeah. All right. What do you think, Lizzie? Is it time? All right. Well, let me see if I can find my share button here and we will get this show on the road. All right. Looks like you should be seeing my screen. And welcome, everyone. Thanks for joining us tonight. Tonight, we're going to talk about EXOS Aerospace and how we're making space available. So EXOS is an integrated pressurized structures company with demonstrated reusable precision sounding rockets. They are considered U.S. munitions, but I'm really proud of our team. In just 14 months, our team of 15 people did complete 4 flights of our Sarge reusable rocket that you see here on the left. We generate revenue as a NASA ready provider. We also serve our Department of Defense, now Department of War, and primarily for research and carrying suborbital payloads to space. We can test things in space before they go on an orbital journey and potentially end up being space junk if they don't work. And we bring it back, and if we hand that experiment back to a university after it's failed, they can figure out that, oh, it was that 13-cent capacitor that just wasn't rated for the vacuum and the cold of space and, say, launch transients. We have served U.S. Air Force when we built a prototype hypersonic reusable launch vehicle, and following on from that contract onto a rotating detonation engine contract. That's actually the vehicle that you see behind me in my background. Now, Scorpius Space Launch Company built carbon composite Type 5 linerless tanks. And as we flew our first launch vehicle, we had 3 very successful flights, and we lost the vehicle on the 4th flight. We had a RUD, rapid unscheduled disassembly. Yeah, not a good day, but that's actually how we celebrated my daughter's birthday one year. It was on October 26th of 2019. We flew to light a candle for her birthday. Unfortunately, the candle had an after flame when the vehicle hit the ground. Root cause, material fatigue. It turns out that aluminum does not like going through max Q and bending over and over and over. And the nose cone actually slipped down into the payload section. So Carbon composites wouldn't have that problem. We knew that early on, but because it cost about 10 times more to build a carbon composite rocket, we figured we'd do our testing on the aluminum one. And that turned out to have been a good decision. So in 2021, of course, COVID was just coming on. We had a DoD contract where we proposed to make our rocket 25% bigger and 29% lighter, all in one fell swoop, while solving our problems with reusable launch using aluminum. And I thought that was great, but I was really proud of the fact that we did integrated pressurized structures with Scorpius. And sorry, I had a few more people who wanted to get in. So we built 100% of the vehicle in-house. And what we wanted to do was maintain that. Well, when we went to Scorpius to have them build our outer structures and tanks, we lost that. So I made a deal. I said, hey, we'll buy 10% of the company today, but if I can put your tank technology on the moon, we get the right to buy the rest of the company at today's valuation. So long story short, February of 24, March of 2025, we put the Scorpius fuel tanks on the moon aboard the Odysseus lunar lander and the Athena lunar lander, both operated and flown under NASA contract by Intuitive Machines. Well, we thought passing NASA qualifications was hard for Type 5 tanks. And then we got to SpaceX, and they were basically making a bet of about what's Falcon 9 cost? $75 million. They were betting about $75 million that our fuel tanks would be good to be fueled with LOX and methane on board the Falcon 9 rocket. That was a bit even more of a challenge than NASA's 150 tests. But they actually fueled this launch vehicle that you see on the screen while it was inside the payload fairings. So pretty cool accomplishment. Makes a huge moat for us because SpaceX has very high standards for any tanks or any structures going on board, even down to their basic is just, qualified to DOT standards. So we did have an independent company come back and say, hey, after you put that tech on the moon, your valuation of the company went up by about 9x. So that was a great day for us. The Type 5 tanks that flew on Odie are affordable. We actually use a trade secret process that allows us to cure the resins at room temperature. Cuts about half of the energy input into a tank. Of course, they're lightweight because they don't have any metal. All composite materials don't rust. We can do unibody builds. And this is really going to change the way we build space vehicles. They can be more lightweight, streamlined, have a more robust structure. And it's all because of that room cure resin. Today, to make a tank and then put structure on it is very challenging because a thin piece of structural material in carbon composite might not cure at the same rate as a tank that might have a thicker wall. So there's problems with that. The unibody build process that we use with these room temperature cure resins solves that. And space eco-friendly because we support sustainable fuels like LOX and methane. Of course, many people are using hydrogen and other cryogenic fuels, but NASA has been looking for this tech and asking for it for 30 to 40 years to get us away from the ever so prominent hydrazine. And hydrazine is a phenomenal fuel, but LOX and methane are about 20% more efficient. So if you want to get somewhere fast, or you want to add maybe a year of life to your satellite, LOX and methane is a good way to do it. So we do have other markets. You know, the space stuff is the most exciting until you realize that we can make medical tanks as well. And a Type 5 medical tank with no metal addresses some of the safety hazards of metal bottles. And they're a lot easier to carry around because you can actually carry a small bottle that clips on your belt with liquid oxygen instead of having that gaseous oxygen tank. And these can also provide positive pressure, which makes it capable of supporting even very, very early born infants in the 20 plus week category, where their lungs, they don't have the capacity to breathe in. These positive pressure systems can help with that, as well as even in ablation surgery, where now we can use these cryogenic tanks to support surgery so that we don't have to stop the heart during surgery. So many advances in the medical field that I think our tanks will be used for as we get through FDA approvals. Of course, conformal hydrogen tanks. Imagine if you could put a tank into the structure of an aircraft, and now you can do that because you don't have to bake it out. And again, those dissimilar structural components aren't as much of an issue when it cures at room temperature. This would be a MRO or a maintenance refit facility type activity, just be licensed. And then even logistics and transportation. Imagine a cryogenic tanker truck that weighs 15,000 pounds less, gets better fuel economy. Again, those are licensing opportunities, but just kind of shows that we go across multiple markets. So the IP cuts our costs in half of making composite tanks. It enables medical tech. We do have some strategic collaborations where we're partnering with companies like Firefly to do Mach TB, and actually the submission today for Mach XL, where people are looking to fly faster with some of the capabilities that we offer. And fortunately, we can build vehicles like we have behind us in just about 9 months on a advanced DoD contracting mechanism. In this case, we're testing rotating detonation rocket engines in flight that NASA has proven on a bench. So big difference between a large, heavy chunk of metal that can survive bench testing. But when you start trying to make things a little more lightweight to put them into flight, do an engine restart as you're descending from altitude, that's where the rubber hits the road, and we prove out some of these technologies in new ways. So there's about a $570 billion market we're going after. We believe we can address about 170 million of that market, and combined between EXOS and Scorpius, which is our tank manufacturing acquisition target, we're running some pretty neat numbers there. Yeah, we have financial overviews for all the fun people, but myself, I've had a little bit of fun in my career. I am, of course, the CEO and co-founder of EXOS Aerospace. Started in submarines, went from the depths of the oceans to the reaches of space, and kind of passed the power industry on my way there. Backed up by David Mitchell. He's the guy who actually taught me how to trade stocks so that I could fire my boss. But he's a fourth generation oil man. He's a broker dealer. He's an entrepreneur himself, has started multiple companies, sold a company to CBS, and has never had to take a salary from his church because he had all these other businesses. Russ Blink is our CTO and co-founder. He's everything rockets. He's developed hundreds of rocket engines along with the rest of the team, built dozens of flying vehicles, including manned rocket racing planes, and even the little flyer you see down there at the bottom where they strapped him into the chair of a vertical takeoff, vertical landing rocket. And then backed up by Neil Milburn, our physics and chemistry guy, who was also very experienced at company turnarounds and writing launch licenses. He actually wrote the rules for us into the Code of Federal Regulations on how to fly a rocket under a crane truck. And I do have a few more people showing up in the waiting room. And so we will admit them. All right, so here we go. Whoops. That didn't work out so well. Let me get back to full screen mode here. All right, so we got past the people part, and Exos is pioneering deep tech ventures. We're leveraging cutting edge aerospace materials technologies, not things necessarily that we build. All of them, we leverage our NASA tech, just like SpaceX and all the smart guys do. And we're developing reusable launch systems, next generation composite structures that are lighter and better for reusability. And we can revolutionize production process in many different sectors, including defense, medical, energy, and really trying to take advantage of the macro shift we're seeing specifically in space and defense. So with that, I think, Lizzie, we're ready to go on to some Q&A that you should have for me. All right, I'm going to ask you to unmute. I think I have to do that because you put me in control. There we go. Now that I've asked you to unmute, does it let you unmute? Oh, okay. Let's see. Make host. All right, you're now hosting, Lizzie, so you can bring
Great.
those questions.
Awesome. Thank you. Okay. Well, thank you guys so much for submitting your questions ahead of time. We've got a great list of questions and we're going to go ahead and jump in. So, John, the first question we have is what problem is EXOS solving that isn't currently being addressed by traditional launch providers?
Okay, well, reaching orbit almost always takes multiple launch attempts. Even teams that are strong, NASA background, it takes anywhere from 3 to 7 flights. That's just kind of historic numbers before you get to what they call reliable orbital access. I do have to shout out to Peter Beck with Rocket Lab. Um, their second flight, they were actually successful. But I think he wouldn't even say that they were achieving reliable orbital access until they got up to that 5, 6, 7 flights. So a first generation orbital launch attempt is normally a 30 to $100 million of cost. And that's broken up between the launch services, obviously range costs, program costs. And when an early flight fails, as many of them do, the consequences go way beyond the hardware. They impact investor confidence, which is one of your big costs. Customer trust, if you had a payload on board and you lost it, and even program momentum. The environment we operate in forces teams to minimize the risk instead of quickly learning through iteration. Now, obviously, Elon at SpaceX has kind of thrown caution to the wind with regard to rapid iteration and learning through failure. He has embraced it, and I don't think the rest of the industry has really done that. But if you don't, it actually stretches your development timelines. It increases the chance of exhausting capital before success, as I've seen far too many rocket companies do. And the real problem here isn't even access to space. It's the cost, the speed, and the visibility of learning that often slows us down on our path to orbit.
Okay,
So
that's
what else you got?
okay. So, how does EXOS solve that problem differently?
Well, Exos moves the early flight learning off of the high dollar orbital rocket and onto a licensed reusable suborbital platform. Instead of putting that 30 to $100 million risk up front, teams access a proven Exos reusable vehicle, and let's just say it's a $5 million wet lease, but your marginal per flight cost to test things is on the order of $100,000 per launch. Even if you do 50 or 100 flight tests, you'd never get near that $30 million. So Exos can enable the team to mature your own avionics, your guidance, your navigation and control, your flight software, prove your autonomous systems. And those are kind of the hardware elements that can be payload on a suborbital flight. But then it gets even better because you actually do the integration with vehicle operations and your ground support equipment. which so commonly you'll get to the flight pad and there's nothing wrong with the rocket, but the ground support equipment doesn't work. We get to test a lot of those things, even on a small scale for an orbital launcher. You run through countdown, launch, recovery, and with a reusable rocket, you can even take the vehicle through a reflight process and understand in the beginning what some of those costs are. And because EXOS vehicles are reusable and already licensed, teams can fly more frequently and sooner. We can recover hardware. We iterate privately without public or investor exposure to the orbital launcher company. And EXOS is currently only one of three in the US with the license to be able to fly that reusable vehicle. So the result is fewer learning flights required on the orbital vehicle, lower early capital demands, and a higher probability of success as you step into orbit. If we could just take that to from 3 to 7 flights for an orbital launcher down to, say, 2 to 6, that can be tens or hundreds of millions of dollars in cost savings with a higher probability of success. So we don't replace orbital launch, we just make it viable sooner.
Okay, fantastic. So there's several questions around the idea of integrated pressurized structures. So how do they change the economics of space systems?
Yeah, I'm glad they picked up on that. I always thought it was about weight savings. And when we built the hypersonic reusable launch vehicle prototype for the Air Force, we told them it's going to be 25% larger and it's going to be 29% lighter. But as we went through that and we started actually hovering and flying that vehicle, tell the vehicle to fly itself 10 feet off the ground, go to four corners, rotate 90 degrees at the corners. We discovered that parts count was more significant than mass as the real cost driver. And the materials that we were using from Scorpius, that was obviously patented and trade secret, those integrated pressurized structures where we were able to combine the pressure vessel, the primary structure, and even cableways and shelves into a unibody system enabled our affiliates' proprietary room-cured resin system to kind of expand our capabilities and reduce our cost structure. So it allowed fully integrated structures to be built without autoclaves or long heat cure cycles. So that capability gave us what we call an embedded load path, fewer parts, faster manufacturing, and most significantly, more rapid reuse. I don't have 3,000 fasteners to go check. And just as a rule of thumb, we look at every component on a rocket as $1,000. I don't care if it's a 2-cent screw or an $80,000 rocket engine. It's $1,000. So if we look at Virgin Orbit's Launcher One, and I can talk about them now because they're bankrupt and gone, they had 40,000 components on their launch vehicle. And granted, that was an orbital class vehicle with 2 stages. We're single stage, suborbital. We're at 4,000 components. And that's not a mistake, that's by design. So the fewer parts, faster manufacturing, more rapid reuse, cuts labor, turnaround time, reduces our life cycle cost, and yes, our overall system weight. But the real savings are there in the fewer components that we actually have to check between flights. The resin system is at TRL-9. It's got lunar heritage. It's sitting on the moon. I don't know of anyone else in the world that has that. And by replacing parts and inspections with these integrated pressurized structures, we fundamentally improve the capability for spaceflight at a better economic price point. Wow, I went on that, didn't
It's an exciting topic.
I?
Integrated pressurized structures. It's a game changer, truly is. Okay, so our next question is why do liquid-fueled US manufactured suborbital platforms matter so much for defense, NASA, and also for commercial users?
Oh, this is a great question because those are our three primary markets: defense, NASA. NASA's kind of government still, but really responsiveness and control drive today's mission values. So traditionally, suborbital testing relied on expendable solid rockets. They offered limited adaptability, and they often required a new vehicle when mission profiles expanded. And we have, of course, as you mentioned, US manufactured liquid fueled reusable suborbital platform. We actually define our flight profiles with software. Um, at altitude, trajectory, payload environments. We can adjust all these between missions without hardware changes. And while we probably can't replace, and I'll use Black Brant as an example, all 12 configurations, even with sub-configurations, but all 12 of those without any change to a reusable rocket designed today, we can use some of NASA's latest tech and we can more cost effectively serve most of those Black Brant missions with one vehicle. And we use what we call dolly lose. Cool, fun word, right? Uh, Day of launch iLoad update. And the iLoads are initialization loads, and they actually set the parameters for our guidance, navigation, and our control. So those are the software things. But then if our rocket is capable of going to 300 kilometers and we only want to go to 150, we just don't put as much fuel in. So now, again, we're serving multiple mission sets. Some of them just software, some of them, yeah, we physically might load less fuel. So for defense and NASA, that means faster iteration. We are using domestic supply chains and we have lower program risk. Pretty much everything we're using is TRL-9 hardware. And when we go out after a new contract like Mach XL, we'll actually use a Firefly engine perhaps, but then we'll use a NASA RDRE as our development chain. And at the end, we'll have, say, an advanced RDRE engine that we could use in addition to being able to use something that's at TRL-9 when we started the program. And that makes lower cost per test.
Awesome. Okay, our next question. Why are flexible suborbital test platforms critical for missile defense systems or things like Golden Dome?
Oh, real flight data wins. Models are great, um, but flexibility beats diversity. And very hypothetical at this point on Golden Dome, but those systems are going to need to detect and characterize vehicles in the first second of flight. And some of the emerging threats don't resemble any traditional boost profile that we've seen before. So hypersonics and those unconventional threats really produce signatures that are based on legacy algorithms. You know, we know what vehicles do off of the launch rail, but as soon as they turn a little earlier, our algorithms will get overwhelmed. They weren't designed to recognize those characteristics or even some of the speeds that we're seeing today. So modeling alone can't close the gap as efficiently as having actual flight data. So a reusable liquid fueled suborbital platform that can actually go out and do hundreds of real flight environmental data tests, flying at a different profile every single day if you wanted to reuse the vehicle over and over, while supporting a faster validation of everything from your sensors to your algorithms and your systems against a measured reality or even proving out that model. Um, yeah, I think I'll leave it at that.
Okay, that's a great answer. I think you hit everything there. Okay, the last question that we have is why does that approach position Exos for long-term success? I'm talking about, well, what we just referred to. I won't take your time.
Okay, so we use a common reusable rocket core, and that can cover in atmospheric flight. So if we're flying trajectories and space missions, while enabling mission-specific capabilities through modular sections. So if we're flying a trajectory, we might have to have a thermal protection system on the nose cone, on the fins, but those are just components that we switch out onto the rocket. Now, the flight systems, avionics, and operations are consistent. Um, those components don't affect how we uh, operate the vehicle. So only those mission specific elements change. It preserves the learning and the operational reliability that we develop as we go from flight to flight to flight, and isolates and reduces risk. So when you combine that with reusability, integrated pressurized structures, software-defined flight profiles, this approach enables high flight rates, literally flying a vehicle every single day if you've got the crew to support it, or even multiple times a day. Right now, we believe with a crew of 10, we can do a flight, turn around, and fly the same vehicle again in 48 hours. So you add a second or third vehicle, and now you're flying every 12 to 18 hours, right? So this also gives us a scalable path from testing all the way through to space flight. So since you said this is the last one, I'll close with that. Thank you for all the questions. We appreciate the opportunity to share how we think we're changing the economics and learning in spaceflight at Exos Aerospace. And by shifting that early development from 30 to $100 million expense into orbital for an orbital learning flight to a $5 million reusable vehicle lease and $100,000 per flight, we believe that iteration is now enabled, and we have faster learning, lower risk, and dramatically reduced capital requirements on the path to orbit, resulting in fewer orbital launch companies going under as they look to explore the stars. So for anyone who wants to go deeper, we'd love to have a follow-on conversation.
Awesome. Well, thank you guys so much for joining us tonight. This has been recorded, so it'll be sent to you tomorrow to watch the recording if you'd like. And if you'd like to continue the conversation with John, you can respond to that email and we will set that up for you. So thank you guys so much, and we hope you have a great evening.
Thanks, everyone. Bye now.